Okay, so today's lecture is the top-level view of computer function and interconnection, and this corresponds to chapter 3 in the Stallings book. So we'll start off with talking about computers these days. It sounds like one of those things like, hey, kids these days, but computers consist of a CPU, memory, and their I/O components, and oftentimes in the von Neumann architecture, we combine the arithmetic logic unit and the control unit into that CPU, or centralized processing unit. The components are interconnected to achieve basic functions, and then we characterize the computer by describing the external behavior of each component. For example, the data and control signals, and then describing the interconnection structure and controls required to manage it. So chapter 3 in this textbook focuses on the basic structure used for computer component interconnection. Those are bus, point-to-point, and PCI Express. There are some other ones that we'll cover very briefly. So let's take a look at section 3.1, computer components. And most computer designs take advantage of the von Neumann architecture, which you've probably heard me beat up on quite a bit up until this point. There are 4 components there: the control unit, arithmetic logic unit, memory, and the input-output. And this is different from hardwired computers such as the ENIAC and the Colossus that comprise the previous generation. Like Legos, there's a small set of basic logic components that can be combined in various ways to store binary data, perform arithmetic and logical operations on that data, as you saw in 266. If there's a particular computation to be performed, a configuration of logic components designed specifically for that computation can be constructed. We can think of the process of connecting these various components and the desired configuration as a form of program. The resulting program is in the form of hardware and is termed as a hardwired program. We'll talk about software programs momentarily, but that's what a hardwired program is. 3 key concepts: the data and instructions are stored in a single read-write memory. Contents in this memory are addressable by location without regard to the type of data contained there. And execution occurs in a sequential fashion unless explicitly modified from one instruction to the next. So, if you have a jump or a jump less than or jump greater than, that will definitely change the order of execution, but generally follow a sequential order. So whether the computer is hardwired or has software is a critical distinction between different types of computer. We talked about Colossus and ENIAC in the previous slide. So instead of rewiring the hardware for each new program, programmer can supply a new set of control signals. That is, the program is a sequence of steps, and in each step we do some arithmetic or logical operation on the data. And for each step, a new set of control signals is needed, and each one will use a unique code for possible configuration for each possible set of control signals. And then we add this to the general purpose hardware, a segment that can accept code and generate control signals. That is a control unit or instruction interpreter that interprets those control signals and then allows us to perform the general arithmetic and logic functions, which is what we're doing when we're programming in software. So software is a sequence of codes or instructions, and part of the hardware interprets each instruction and generates control signals. That's typically the control unit. Provide a new sequence of codes for each new program instead of having to rewire the entire machine each time. Major components in the CPU are the instruction interpreter and the module general purpose arithmetic and logic functions, or the arithmetic logic unit. I/O likewise has major components: the input module, which contains basic components for accepting data, instructions for converting them into an internal form of signals used by the system, and an output module, which is a means of reporting the results external to the computer. Several other components are needed to yield a functioning computer. Data and instructions need to be put in the system with the I/O, and we need some form that we can read it out. We're also going to need one more thing, and that's memory. Or perhaps I already mentioned that. But an input device will bring instructions and data in sequentially, but programs are hardly ever executed sequentially. You jump around a lot. You'll remember the jump or jump less than, jump greater than, jump equal to signals that you had in basic assembly programming. Similarly, operations on data can require access to more than just one element at a time in a predetermined sequence. So there needs to be a place to store both instructions and data temporarily. And that module is called memory or main memory to distinguish it from external storage or peripheral devices. Von Neumann pointed out that the same memory could be used to store both instructions and data. And that's really important. The CPU exchanges data with the memory. For this purpose, it typically makes use of two internal registers. One is a memory address register, or an MAR, that you see up there in the upper left. That specifies the address in memory for the next read or write, and a memory buffer register, which contains the data to be written into memory or receives the data read from memory. Similarly, an IO address register, or IOAR, specifies a particular IO device. An IO buffer register, IOBR, is used to exchange the data between the IO module and the CPU. So we could look at the components in this type of top-level view. A memory module consists of a set of locations defined sequentially by sequentially numbered addresses. Each location contains a binary number that can be interpreted as either an instruction or a piece of data, depending on what you're doing with it. An IO module transfers data from external devices to CPU and memory, and vice versa. It contains internal buffers for temporarily holding these data until they can be sent on. And so there you can see kind of a more complete view of these components and their interconnection via the system bus. So the other thing is computer function. And we talk about structure and function a lot. So the basic function of the computer is to run programs. At the simplest level, you can view the work of the computer as fetching and executing instructions. That's a two-step cycle. It really amounts to fetch, decode, and execute, but I think Stallings is just beginning with a simpler view of this here. So let's look at fetch and execute. At the beginning of each instruction cycle, the processor fetches an instruction from memory. The program counter, or PC, holds the address of the function instruction to be fetched next. The processor increments that program counter after each instruction, so it'll fetch the next instruction in sequence. The fetch instruction is loaded into the instruction register, and then the processor interprets the instruction and performs the required action. And these actions typically fall into processor to memory or vice versa, where data can be transferred from the processor to memory or from memory to processor, processor to or from IO, data processing, where you perform some arithmetic or logic operation on the data, or a control, which alters the order of execution. For example, the processor may fetch an instruction from location 149, which specifies the next one should be from location 182. The processor will remember that fact by setting the program counter to 182. Thus, on the next fetch cycle, the instruction will be fetched from location 182 rather than 150. And instructions execution can involve a combination of these various activities. So let's take a look at an example. Consider a machine that has a single data register called an accumulator. Data and instructions are given in 16 bits, and it uses 4-bit opcodes. So if you have an instruction, it will have an opcode followed by an address, and a partial list of opcodes are given there. 0001 is load the accumulator from memory. 0010 is store the accumulator to memory. 0101 is add to the accumulator from memory. If there's a actual value, then it will have a sign and a magnitude notation in this hypothetical machine. We'll talk about different ways of dealing with numbers beyond sign magnitude, and you'll probably be familiar with 2's complement from 266. So how would you execute a program? Let's take a look at how you would execute this program here. And you can see we've loaded this with decimal numbers rather than just binary, and that's going to make our task a bit simpler when walking through this program. So let's start at the beginning, step 1. And we begin in the upper left. The program counter contains 300, which is the address in memory. The instruction is stored as 1940 in hex. The instruction gets loaded into the instruction register, and we increment the program counter. So that 1940 goes into the instruction register. The author writes this in hex, so the first 4 bits correspond to the first hex digit. That's 0001 in the instruction register to load the accumulator with the contents of address 940. Then we fetch the next instruction, which is 5941, into the instruction register from location 301, and then increment the program counter to move it to 302. So instruction 0101, which corresponds to 5 in hexadecimal, says to add the contents of the address 941 to the accumulator. So we've added a total of 3 plus 2, that's equal to 5 in the accumulator. Next instruction 2941 is fetched from location 302 and loaded into the instruction register. The program counter gets incremented to 303. And instruction number 2, which is 302, says 0010, which says to store the value from the accumulator in location 941. So 5 gets transferred from the accumulator into 941. This took 3 cycles, but different machines may require different amounts of instructional cycles. So here's the instruction cycle diagram. You started the instruction address calculation and proceed through the maze. So start there in the lower left. You have the calculation of the address. You fetch the instruction, decode it, figure out the operand address calculation, and fetch the operands if necessary, perform the data operation, and then figure out whether you need to store that operand with an operand address calculation and store. And if you don't need to store or you're finished storing, you go back to the instruction address calculation. So almost all computers provide a way to interrupt normal processor operations. And these are an efficient way to improve I/O. Since again, I/O can be a bottleneck. Think about printing a 100-page document. And if you had to wait until that was done in order to proceed to the next instruction. And there are several types of different interrupts. This is an interrupting cow here, and the joke is knock, knock, who's there? Interrupting cows. Interrupting cows, yet. Here's a set of different types of interrupts. There can be program interrupts that generated by some condition as a result of instruction execution, arithmetic overflow, division by 0. These are your classic ones that cause problems in your programs. Timer interrupts allow the operating system to perform certain functions on a regular basis instead of just purely running the program. I/O is probably the most frequent one, which is generated by an I/O controller to signal the completion of an operation, request service from the processor, or to signal a variety of error conditions, such as a PC load letter. And last but not least, you can have an interrupt for hardware failure. So the idea is that the processor wants to do other things besides waiting for I/O to finish up. So a program with 3 writes, in the upper third, there's no interrupt. So you have the program, it runs for a bit, then you need to write, which requires an I/O program, I/O command, and then that ends, it transfers back up to the end of that write, and then proceeds to execute part 2. And after part 2, it needs to do a little bit of I/O, so it goes back down to 4, then to 5, and then back up to the start of 3, and then we'll finish up, and at the end there will be another write. So a middle interrupts that require only short bits of I/O. So here we would have 1 followed by a little bit of I/O going back up and finishing that write, then doing 2A, and then in the middle doing a little bit through the interrupt handler, a little bit more I/O from that previous operation, going back up and doing 2A. And the same thing would happen in 3. The lower program is one with longer I/O waits. So the user doesn't need to contain code to accommodate interrupts. So when you write your program, you don't need to accommodate those. To deal with them, we add an interrupt cycle to our original instruction cycle. The processor suspends execution of the current program and saves its status. It sets the program counter to the start of the interrupt handler routine. And when the interrupt handler is done, the processor returns to its original program. So it divides it up in a way that you don't see that it's actually doing it rather than doing a long IO operation. Now, what happens when you have more than one interrupt? Well, there are two approaches. One, you can disable interrupts if you've already got one in progress. That's simple to implement and not too bad to think about. Things are in order, but it doesn't deal with relative priority. So, you can't do a prioritization of them, that, hey, my printer, my mouse is more important than my printer. You can also set priorities for interrupts, so the most important tasks get done first. It's a bit trickier to implement, but it's going to give you a bit more efficiency. So we can have IO modules that exchange data directly with the processor. The processor can read data from or write data to an IO module, and then the processor identifies a specific device that's controlled by a specific IO module. IO instructions rather than memory reference instructions. In some cases, it's desirable to allow IO to occur directly with the memory. So those exchanges happen with the memory component. The processor grants an IO module the authority to read or write to memory so that the IO memory transfer can occur without tying up the processor. You don't have to send that memory to the processor. You can send it to the IO controller instead. The IO module will issue read or write commands to memory, and that relieves the processor of the responsibility of the exchange. This operation is known as direct memory access, and that's pretty important for IO. So here's our revised instruction cycle with interrupts. We do the address calculation, instruction fetch, do decoding, get the operands, perform the data operations, and do the storage. And at the end of that, we do an interrupt check. And if there is an interrupt, then we deal with that interrupt. Otherwise, we go back to the instruction address calculations. So interconnection structures are the way that the different components of the computer are connected. So we have the IO, processor, and memory, and each one will have different forms of input and output. We need to have a way of allowing these to communicate with one another, and this is the interconnection structure. And that's the collection of paths connecting the various modules together. So how do we connect the memory to the IO module to the CPU? So the previous slide shows the data that we need to exchange from each one of those components. The interconnection structure needs to support the following types of transfers. We need to go memory to processor, processor to memory, IO to processor, processor to IO, and assuming direct memory access, IO to or from memory. And this figure isn't in the book, but the textual details can be found on page 100. So one way to do this interconnection is a bus, and the other is point-to-point. Let's talk about the bus interconnection. Full marks to whoever created this monstrosity of a robot. It was filed under bus, I believe. Bing found it for me. So the bus was the most dominant way of interconnecting components for decades. While point-to-point has taken over, you can still see bus interconnections in embedded systems. And a bus is a communication pathway connecting two or more devices. They have a shared transmission medium, and only one device can transmit at a time. A system bus is a bus that connects the major components, for example, processor and memory. So a bus is just a communication pathway between two or more devices. So let's talk about bus interconnection. The key characteristic is that it's a shared transmission medium. Signals can be transmitted by any one device. They're available for reception by all other devices that are attached to the bus. If two devices transmit during the same time period, their signals will overlap and become garbled. So only one can control the bus at a time. And it typically consists of multiple communication lines on the bus. Each line is capable of transmitting signals representing binary zeros and ones. Computer systems contain a number of different buses that provide pathways between components at various levels in the system hierarchy. And the system bus is the one that connects the major components. Most common computer interconnection structures are based on the use of one or more system buses. And there are three different types of buses: data, address, and control. So let's talk about the data bus. These are data lines that provide a path for moving data among system modules, and they can consist of 32, 64, or 128 separate lines. The number of lines is referred to as the width of the data bus, and the number of lines determine how many bits you can transfer at a time. The width of the data bus is a key factor in determining your overall system performance. Again, that designing for performance subtitle of our texting course. The address bus is used to designate the source or destination of the data on the data bus. If the processor wants to read a word of data from the memory, it puts the address of the desired word on the address line, and the width determines the maximum possible memory capacity of the system, which again is a performance factor. We also use the address bus to address I/O ports, and the higher order bits are used to select a particular module on the bus, and the lower order ones select a memory location or an I/O port within the module. Last but not least is the control bus, which is used to control the access and the use of data and address lines. Because the data and address lines are shared by all components, there has to be a means of controlling their use. So control signals transmit both commands and timing information among the system modules. They indicate the validity of the data and the address information, and they specify the operations that you're going to be performing. In other words, it says who or what can use the data and the address bus. So if one module wishes to send data to another, it needs to do two things. One is obtain the use of the bus through the control signals, and then transfer data via the bus. If one module wishes to request data from another module, it needs to obtain use of the bus, transfer a request to the other module over the appropriate control and address lines, and wait for the second module to request control of the bus and send that data. A newer way to do things is point-to-point interconnect, and the principal reason for the change was the electrical constraints encountered with the increasing frequency of wide synchronous buses. At higher and higher data rates, it becomes pretty difficult to perform the synchronization and arbitrary functions in a timely fashion. Conventional shared bus on the same chip magnified the difficulties of increasing bus data rate and reducing latency to keep up with processors. The point-to-point interconnect has lower latency, higher data rate, and better scalability. So, and the other thing to note is synchronizing wide buses and multi-core chips also creates difficulties with bus interconnections. So, quick path interconnect is from Intel, and it was introduced to help lower latency, increase the data rate, and give better scalabilities. Significant changes of QPI was there were multiple direct connections, a layered protocol architecture, and synchronized packet transfer. So in terms of multiple direct connections, there were direct pairwise connections to other components. So they were connected in pairs to one another. The processor level interconnects using a layered protocol rather than simple use of control signals. And then data are sent as a sequence of packets, each of which has control headers and error control. So QPI on a multi-core computer is illustrated here, and this shows QPI on a multi-core computer. The links indicated by the green arrows are pairs in the figure. So you can see core A is connected to and from the I/O hub. Core B is also connected to and from the I/O hub. There's no connection necessarily between core A and core B, but core C is connected to core B, and core D is connected to core A. Likewise, core C and core D are interconnected to one another, and core C and D are also connected to the I/O hub. So if you were going from core A to the I/O hub, you might go through core D and then down to the I/O hub. And the I/O hub has the point-to-point interconnect, or PCI Express, to the I/O devices. The cores have point-to-point to the different RAM, and the I/O hub has point-to-point to the I/O devices up at the top. So there's a multi-core configuration using QPI, and the QPI ones are in green, the direct connections, between the pairs of processors, and it's also able to connect to the I/O hub. So actually, I misspoke there a little bit ago. Core A can go directly to the I/O hub up at the top. We also mentioned the layered protocol. It's a 4-layered protocol. The physical are the actual wires. The unit of transfer is 20 bits, which is a FIT. The link is the transmission and flow control, and there the unit of transfer is 80 bits, which is called a FLIT. The routing is the framework for directing packets through the fabric, and the protocol is a high-level set of rules for exchanging packets of data between devices. Here's the physical layer, and it consists of 84 individual links. The lanes are, each data path has a pair of wires that transmits data 1 bit at a time, and there are 20 data lanes in each direction. That gives us 6.4 giga transfers per second, which means 16 gigabytes per second, and it's 32 if you go bidirectional. The link layer is responsible for transmission and flow control. Basically, it performs these at the FLIT or 80-bit level, and typically the message is 72 bits with an 8-bit error code. The flow control function ensures that you don't send data faster than you can receive it via credit scheme. The error control checks for errors via an 8-bit CRC value. And then last but not least, the routing layer is pretty much what it says on the tin. It's used to determine the course the packet will traverse across the available system interconnects, and that's defined by firmware and describes possible paths the packet can follow. The protocol layer is the rules for exchanging packets of data between devices. The packet's defined as a unit of transfer, and one key function performed at this level is a cache coherency protocol, which deals with making sure the main memory values held in multiple caches are consistent. Typical data packet payload is a block of data being sent to or from the cache. Next is PCI, or peripheral component interconnect. That's a popular high bandwidth processor independent bus that can function as a mezzanine or peripheral bus. It delivers better performance for high-speed I/O subsystems. And Intel began to work on this in 1990, but actually was pretty cool and released the patents to public domain, and they're now maintained by the PCI Special Interest Group. So it's a point-to-point interconnect scheme intended to replace bus-based schemes such as PCI. The key requirements are high capacity to support the needs of higher data rate I/O devices, gigabit Ethernet, etc. So we, definitely are achieving higher data rates with our devices. Another requirement deals with the need to support time-dependent data streams. So there's a chipset that connects the processor and memory subsystem to PCI Express, a switch which manages multiple PCI streams, endpoint, which is an I/O device or controller that implements PCI, and a bridge, which allows the older PCI devices to be connected to newer PCIe systems. And PCIe endpoint is an I/O device or controller that implements PCIe, such as a gigabit Ethernet switch, a graphics or video controller, disk interface, or a communications controller. And it's also layered just like QPI, which is the quick point interconnect. And it's a layered protocol. There's a transaction, data link, and physical. And the physical are obviously the wires. The data link is responsible for transmission and flow control. And the transaction receives read and write requests from the software above the transmission link and creates request packets for transmission to a destination via the link layer. And it supports 4 different abstract space, 4 different address spaces. One, the memory space includes the system main memory and PCIe I/O devices, and certain ranges of memory addresses map into those I/O devices. It also has a configuration, which is an address space that enables the transmission layer to read-write configuration registers associated with I/O devices, and the I/O address space is used for legacy PCI devices, with reserved address ranges used to address legacy I/O devices, as I mentioned. And finally, message And this address space is for control signals related to our interrupts, error handling, and power management. So next time we're going to start looking at cache memory.